Hello, George Romanic here. Today we have an amazing problem related to the Coriolis force and a result that will definitely surprise you. Today we are going to talk about geostrophic wind, and geostrophic wind is a balance between the pressure gradient force and the Coriolis force. In the Northern Hemisphere, geostrophic wind blows parallel to the isobars with high pressure to the right of the wind and low pressure to the left side of the wind. In today's problem that you see now on your screen, we are asked to calculate the latitude where the wind is blowing, geostrophic wind is blowing, if we know the pressure gradient and we know geostrophic wind. And the problem says that the meridional pressure gradient is negative 2 millibars per 100 kilometers. So, if this distance is 100 kilometers, then the pressure gradient delta P, delta Y, and Y, because this is meridional, we said, so this is Y direction, is equal minus 2 millibars over these 100 kilometers. So when I move from here to here, and these are isobars, the pressure dropped for 2 millibars. And we have wind that is blowing like this. And velocity U is minus 10 meters per second. Negative because this is positive zonal direction X. So we see that here we have P and here we have P minus delta P, which means we are in the Southern Hemisphere. In the Southern Hemisphere, this geostrophic wind, UG, blows parallel to the isobars, but high pressure is to the left and low pressure is to the right. And you can clearly demonstrate that because for this parcel of air, pressure gradient force is acting from high pressure to low pressure, but in the Southern Hemisphere, Coriolis force is deviating motion to the left, like so. So the balance, so this is Coriolis force. So the balance of these two forces results in the geostrophic wind having only U component in the negative X direction. Positive X is towards the east. Of course, all these are covered in my previous videos. I'm not introducing anything new here. So the question is, given this pressure gradient, and given that UG is minus 10 meters per second, what is the latitude phi, latitude where this is happening? Well, we can already see that this latitude better end up being negative because we are in the Southern Hemisphere. To calculate this, we use the equation for geostrophic wind that I derived. So UG is equal minus 1 divided by FG, F rho, not G. F rho, density of air. And density of air was given to be 1 kilogram per cubic meter. So 1 divided by F times rho, delta P, delta Y. This is the U component of the geostrophic wind, but of course we approximate this using finite differences, minus 1 over, let's say, rho F, switch for no particular reason, delta P, delta Y. So we know that phi F, Coriolis parameter, is 2 omega sine phi, where omega is angular velocity of the Earth and phi is latitude that we need to find. So that means that sine phi is equal, when I plug this over here, oh my god. So it will be equal negative delta P delta Y divided by 2 omega times rho times UG. I hope I did this correctly in my head. So when I substitute F over here, I will get rho 2 omega sine phi. And then sine phi is equal this divided by rho divided by UG and divided by 2 omega. It should be correct. Okay, so now let's calculate this, but we need to express this in SI units because this is given as 2 millibars per 100 kilometers. So delta P delta Y is equal to 2 millibars per 100 kilometers, rather minus. But millibar, we know, is hectopascal, so it's 2 hectopascals over 100 kilometers. That is 100 times 10 to power 3 meters. Or, this is further equal, minus 2 hectopascals is 2 times 10 to power 2 pascals divided by 10 to 3 and 2, 5 meters. Or, finally, delta P delta Y is equal minus. Notice that this will cancel and here I will end up with 3. So I will end up with 10 times, 2 times 10, and this 3 when it goes up will become minus 3 pascals per meter. Okay? So now I converted this in nice SI units, and we also need to know that omega, angular velocity of the Earth, is 7.3 times 10 to power negative 5 second minus 1. Now I can plug in all these numbers over here to get that sine phi, and I will write the numbers, is equal minus delta P delta Y is this, minus 2 times 10 to power negative 3, and I will omit units, everything is in SI units, divided. In the denominator we have number 2 times omega 7.3 times 10 to power negative 5 times rho, but rho over there, look, is 1 kilogram per cubic meter, and UG is minus 10. And we have 3 minuses, which means 2 of them will cancel, third one will survive, which means this angle, sine of angle will be negative, which means angle will be negative, arc sine will be negative, which is good because we need negative angle, we are in the Southern Hemisphere. So now if we take a calculator and you crunch these numbers, the result is the result that I got here is minus 1.3699. What is wrong with this result? Well, sine of an angle is limited between minus 1 and 1. Sine function looks like this, and it goes between plus 1 and minus 1. So there is no way I can get something that is lower than -1. Sine function just doesn't operate like that for real numbers. So where is the mistake? Did we mathematically make some mistake? No. Think about it. Where is the mistake in this problem? I told you that the result is very surprising, as you can see. You get abnormal result. What here is abnormal? Well, in your everyday courses in atmospheric sciences and oceanography, you are usually given this. They would tell you this is pressure gradient. Delta P, delta Y is, let's say, -2 millibars per 100 kilometers. They give you this, and they give you latitude. I don't know, -30 degrees south, 30 degrees south. They give you latitude, they give you pressure gradient, and then they tell you calculate UG or VG. Think about it. They gave you pressure gradient and they gave you geometry basically of our planet. For that, calculate U component. Here, I did something else. I said, I am giving you geostrophic wind component, I am giving you pressure gradient, find this latitude. Well, because this is balanced flow, means Coriolis force, which is effect of Earth's rotation, needs to balance pressure gradient force. For this, now this is extremely important sentence. For this pressure gradient and this value of geostrophic wind, the effect of the Earth cannot balance this pressure gradient force. The Earth is simply not spinning fast enough to provide this balance. And physics and mathematics take care of that, giving you abnormal result. So one more time, this balance is not possible. The setup of the problem is not correct. You cannot have this pressure gradient, 2 millibars over 100 kilometers, and this value of the geostrophic wind in the U direction and this value of air density on our planet Earth. Because our planet Earth has this angular velocity and spherical shape and so on, Coriolis force is simply not capable of balancing this pressure gradient force. So let us immediately introduce part B of this problem to find, for the same setup, what needs to be the highest value of this pressure gradient so that the flow can be balanced. Text is now on your screens. Well, to solve that, I will again go back to this equation. So this equation tells me that delta P, delta Y, which is now unknown, is equal minus rho times F times UG. Now, what is F is 2 omega sine phi. The highest value of F is at either south or north poles, where, so F is equal to omega for the north pole, because sine of 90 degrees is 1, or F is equal minus 2 omega for the south pole, because sine of minus 90 degrees is minus 1. So F cannot exceed 2 omega in absolute values. So the highest effect of Earth's rotation is 2 omega, and I will use minus 2 omega because the problem here is related to the Southern Hemisphere. So I will plug in minus 2 omega here. So delta P, delta Y is equal minus minus rho minus 2 omega times ug, or delta p over delta y is equal to rho omega of the earth ug, or this is equal, so 2 times rho is 1, omega 7.3 times 10 to power negative 5, and times ug is minus 10. So the result again will be negative, which is correct. So if you crunch these numbers, you get that delta p delta y is equal, where is my, you get that this is equal minus 0.0015 pascals per meter. But of course, we want to express this again as millibar per 100 kilometers. And this would be minus 1.5 millibar or hectopascal per 100 kilometers. Okay? And this has to be over the South Pole, close to South Pole, because we used F negative 2 omega. So this problem would have to have set up where the pressure gradient is not 2 hectopascals over 100 kilometers, but at a maximum, in absolute values, but at a maximum 1.5 millibars or hectopascals per 100 kilometers for Coriolis force to be able to balance that pressure gradient that is causing the pressure gradient force. So the goal of this problem is to tell you that pretty much if you are given pressure gradient and latitude, you are always safe. You can find geostrophic wind that corresponds to these values. But you cannot just throw any geostrophic wind and any pressure gradient and expect that there is a latitude on our planet that will be able to balance, that will be able to have Coriolis force that will balance the pressure gradient force. Until next video, goodbye.